I heard things like Star Wars. That's fine. Okay, Newton. He had three laws. Mass times acceleration. What else? Earlier, I heard free body diagram.
Vectors.
Mm-hmm. Vector. Anything else that's not up there that you think? Okay. So, first of all, we have lots and lots of physics that's used kind of inappropriately in sci-fi movies. But hey, we sometimes come up with cool technology in those ideas, and we get cell phones and things like that in the future. So, Newton's three laws. So there's like a first one, a second one, and a third one, right? Does anybody remember anything about the first one? You are just kind of used to already knowing a little bit of this, but this is the law of inertia. This one is that the sum of the forces is equal to ma, and that's a sigma symbol that means summation. And the third is that for every force there's an equal but opposite directed force between two bodies. The action-reaction one. Okay. Now, we probably think mass times acceleration because of the second law. Now, free body diagrams, it's how we express how the forces are acting on the object. Okay? And we use that free body diagram to create our forces equation. Okay? So, first, I like to think of the first law as the law of equilibrium. All the forces are balanced. I like to think of the second law as if it's not in equilibrium, I don't know what else to call it besides non-equilibrium. So we're going to start with exploring equilibrium. So if we can get our forces all balanced and look at that situation, and then we'll move into non-equilibrium situations. Okay? So today I want you to explore with some equilibrium. So if a system is in equilibrium, so let's say there is a object and it is hanging from a string that's attached here, and it's attached to a ceiling or something, and attached here. So here's the ceiling. I think I spelled that wrong, but I don't care. And then here's the floor. Is that object in equilibrium? The sign or whatever that's hanging out there, is it in equilibrium? Sure. And so can you tell me what is the resultant forces? If it's in equilibrium, if you sum up all the forces, they should equal 0. Okay? Equilibrium, balance, just like chemistry uses that word, equilibrium, things are balanced. Okay? Now, in this case, this is a string here and a string there, and the floor, so that means there's an earth acting on it. Okay? And we'll get into some of that in just a minute. But what force or forces, if I was to draw my free body diagram, what force or forces acting on that body?
Gravity.
Okay, the force due to gravity, that's right. So remember, I'm really picky about the word gravity. because the word gravity to me just means that it can be an acceleration, it can be a phenomenon that you're talking about, because mass attracts mass. Who knows why? Nobody yet. And or it could be some force. So I'm going to be real picky and ask you to qualify your use of the word gravity. And then, so what about this? Would there, okay, so maybe a tension force, Ft, and maybe another tension force this way, and pretend I drew those just right. What would be the case if those two forces were equal? What must be true?
Then if Ft equals Ft, then Ft equals 4.9.
Does it matter?
No. Yes.
No, you're. Just a second.
Okay.
So the gravitational force is not going to change. What would have to be true about the way these are pointing? I'll give you some more clues. The angles have to be the same. So the angle between the horizontal and the velocity vectors. So if I want these two forces to be equal, then they have to be at equal angles to the horizontals. Okay, that is a statement. But what if I'm going to call the left one theta 1 is greater than theta 2? So that means that your picture might look like force tension 1, force tension 2, gravitational force, and this would be theta 1, and this would be theta 2. What would be true there? Force tension, what's the relationship between force tension 1 and force tension 2? Or that's what you think, right? Now what is this F sub G business?
Force due to gravity?
Yes, it is the force due to gravity. Whoops, I forgot the do word. Does anybody know how to calculate the gravitational force?
Gravitational acceleration is 9.8 meters per second. Force equals mass times acceleration, so you need the mass of the body. So multiply the you gravitate. Yes, you multiply the gravitational acceleration by.
Gravity is a field. Okay, it's a field that's pointing towards the center of the Earth all the time. So if I make a circle to represent the Earth, there is a gravitational field, and I'm going to use little vector symbols. Anytime you're using an arrow, that means that the quantity you're describing is a vector. So you can almost test out to see, oh, is this quantity a vector or not? Does it feel right to put an arrow on it? So there's a gravitational field around the Earth. Now, if I put an object right here, that object will, if I let go of it, it will accelerate down. If I'm holding it, I will feel a push on my hand that I'm holding that object. Okay. Now, there's no object right here. There's just a blank space that I have made with my little dotted dot lines. So, is there a field there? Yeah, there is still a field there. Okay? There's just not anything the field is acting on. Okay? So, the way field forces work is a field force applies a force to a particular particle. So, a gravitational field applies a force to a mass. An electric field applies a force to a charged object. Not a neutral object, but a charged object. A magnetic field applies a force to a moving charged object. So fields apply a force to a particular type of particle or object. So because there is mass and it is in a gravitational field, there will be a force on it, and we call that force the weight force. So it's just like the weight you've learned before, I'm just giving you more detail and exactly what it means. Okay? So this little g actually represents the gravitational field constant.
As in Earth's gravitational field constant?
As in whatever planet you're on.
And we assume we've been told otherwise.
Yep. We'll be on Earth unless you're told otherwise. Okay, so if a force, now remember, Newton was a really important dude, so what is the unit for force? A Newton will have to be equal to, and this is what you're telling me mass, which is in kilograms, times this, whatever our g is measured in. So what would the unit for the gravitational field constant be?
Meters per second. Well,
Newtons per kilogram. So if you take an object and weigh it, find its weight, you will find that that is the mass of the object times a constant. And then for the Earth, I'm going to make a little error. That's not an equal sign. That's just the next thought is g for the Earth winds up being about 9.81 meters. Nope. I don't want to use meters per second. But it winds up being about 9.81. And I like to use newtons per kilogram as my unit here because it reminds me that I'm using the gravitational field to apply a force, not to be an acceleration. So that's why I like to use that unit. Yeah, so let's go back up here and look at this one. The force tension 1 is more vertical. Therefore, it should be greater. You're exactly right. It's holding more of the weight. So, this seems like some sort of claim that the force tension 1 is greater than force tension 2. So what we're going to do is I have these things called force tables. And so imagine you're looking at a side view of a table, and it has legs. Okay, and there's a little pin on top, and there's even like a compass type angles measured around the side, and there's a ring that will go around the peg, and we can attach strings to that ring and then hang mass over the edge. And we can attach a string to this side and hang a mass over the edge. And oh, you can't see it because of perspective, but there's the mass hanging back there. So if you look overhead, you see the ring.
Wow, your art skills are fantastic.
Thank you. And so then you might see something like this, and then it disappears because we can't see the edge of the can't see below the tabletop there. And then this one, and then maybe that one. So that's what we would see looking over top.
Oh, baby.
So if we hang a mass here, M, what is the force in this string if we're in equilibrium and nothing is moving?
The force of that string is 9.8.
It would be, so there would be a tension force up on our hanging mass. There would be the weight force down on it. If it's in equilibrium, the sum of the forces would be 0. So the tension force would be equal to the gravitational force, the weight. So what we're going to do is experiment with which of these forces is bigger. Is it that T1